So let us formulate this now. So mathematically, by the way, we are solving a constraint optimization problem now, right? So we want to minimize or maximize and optimize a particular function such that something happens, correct? Now what is our objective function here? Objective function is maximize, or let us say minimize norm w by 2, just take the inverse with respect to w, we want that w, right, that is our parameter, okay, such that, is this an unconstrained problem? It is not an unconstrained problem, there is a constraint. What is the constraint? Huh? No, not mathematically, tell me in English, what is the constraint? Exactly, no point should be misclassified on data, right? You need to learn a discriminant function, decision boundary. So how do we write that? Such that W transpose xi plus b times yi is greater than or equal to 1 for all. So this is the problem that we solve in an SVM. Okay. So please look at this, it is very interesting. In our ERM, loss was a function of h, the parameters x and y, correct? The constraint was in terms of parameters. Now we have swapped it. The objective function is with respect to the parameters, the constraint is with respect to data and labels. So it does not matter, because finally when we write the Lagrangian, right. So this is ERM with regularizer. As we will see later, SVM or max margin classifier is actually an ERM with a particular type of loss function called the hinge loss. This is called hinge loss and L2 regularizer. This regularizer is always on W, no? When you write the Lagrangian, how does our loss function look like, right? It is some function of h comma y, right? This is what it is, plus some lambda times some regularizer on W. This is exactly what it is. This L is of this particular form. I will write that. See, I can swap it, right? I can write that this is my optimization problem and this is my constraint, because when I write the Lagrangian, it is simply function 1 plus lambda times the constraint. How does it matter if that is it only depends on what is the space on which you are optimizing. Anyway, you are optimizing on the parameter space. So in SVM, a max margin classifier is empirical risk minimization, okay, with linear hypothesis spaces under the hinge loss with an L2 constraint on parameters. Got it? But the good thing is that we do not have to resort to numerical methods to solve this optimization problem. There is a nice analytical way to solve this. So that is what makes this SVM very elegant. You do not need a gradient descent to solve this. Do you see that already, that this looks like a loss function and this is the regularizer on the parameters, okay, right, okay. Now we have to solve this optimization problem. Again, we need to solve a constraint optimization problem. How do we solve this? Lagrangian, and I told you in the last class to look at these things called Tucker conditions, KKT conditions, right? If you have a constraint optimization problem, when you solve it, you will have to write down something called Tucker conditions, KKT conditions. Let us write that for this. So the above problem is a constraint optimization problem See, the elegance of this entire thing comes because of two things. One, constraint optimization problem with convex cost and linear constraints. You see this? We are the optimization problem is over W, okay, and the objective function is convex because we are looking at 2 norm. Okay, what we are trying to optimize is norm 2, which is convex. The constraints that we have, okay, in terms of W are linear. So we are solving a convex optimization problem, okay, with linear constraints. That is what makes it elegant. So we have very nicely formulated standard optimization procedures to solve these kinds of problems, right? Convex problems with linear constraints. And can somebody tell me how many constraints do we have here? As many number as there are number of data points. Okay, yeah. So we'll have to solve this above constraint optimization problem. To do this, solve the above via KKT conditions. Okay, just for the sake of completeness, I will simply mention what these KKT things are. So you have a constraint optimization problem. First you write down the Lagrangian, okay. You write down the Lagrangian and there are 3 or 4 conditions which are called the concurrent KKT conditions. I mean, one of which is known to everyone. Whenever we are solving an optimization problem, we know that the derivative of the objective function has to go to 0, right? That is one of the conditions. So like that we have 3-4 other conditions that we will write down and we will use the KKT conditions, okay, and we formulate what is called as the dual problem. There is something called duality in optimization, which means that for every primal problem, okay, there exists a dual problem in the dual space, right, where the constraints and the object, I mean the optimization variable gets swapped, okay. So we can solve both the primal and dual problem simultaneously to find the solutions for both the primal problem and dual problem. That is what we will do. So what we will do is the entire process is as follows. We start with this problem, write down the KKT conditions, okay, and then we write the dual of this. The dual always of a primal problem will be an optimization problem over the Lagrangian multipliers, always, correct. And then we show that the dual problem can be solved using standard solvers. So what will be solved finally in an SVM is the problem in the dual domain using standard solvers, standard optimization solvers. Once you get the Lagrange multipliers, you can always come back to the primal domain, plug them in and find the W and B. That is the whole idea. We will write down this W and B, the optimal W and B, in terms of the data points and the Lagrange multipliers, optimal Lagrange multipliers. You understand? The first step is to show that the optimal W and B will be a function of the data and Lagrange multipliers. Okay, that is what we do by writing KKTs. And then to get those Lagrange multipliers which are needed to find the optimal W, we solve the dual problem. That is the idea. That is all we will do now. Okay, so let us write them all one by one. So first of all, let us write the Lagrangian. I can't emphasize this, emphasize on this enough. See, learn 3 math tools very well and you can do all ML. Probability theory, okay, little bit of matrix calculus and optimization. That is all. Everything is an application of these 3. Okay, so all machine learning is simply application of these 3 ideas, as you have seen already. Right? You need to know how to optimize, you need to know how to deal with density functions, that is it, yeah. Okay, so define Lagrangian for this. So Lagrangian L, this will be a function of the variable upon which we are solving the optimization problem and Lagrange multipliers, let us call them as mu. Okay, this is equal to the constraint which is norm W the objective function which is norm W plus, come again, by 2, we can ignore that, it's okay, because that's a scale, no, we'll leave that out actually, plus, okay. So how does the Lagrangian look like? There is one Lagrangian multiplier corresponding to each of the constraints, correct? So that would be 1 minus, no, let's write the constraint, no, 1 minus, okay. So first of all there is a sum over all the data points, because every data point is a constraint, and the constraint is 1 minus yi times W transpose xi plus b. Why is this? See, this can be rewritten as 1 minus W transpose xi plus b times yi. Typically this is how you write the linear constraints, right, less than or equal to 0. So this is what it is, and this multiplied by mu I. So every constraint has a Lagrangian multiplier associated with it, right? This is the objective function. Okay, actually I was wrong about it. We want that 2 otherwise algebra won't work out. Okay, W transpose W by 2, come again. Yeah, here there is a B as well. Yeah. Where? This one. W transpose W is, right? Yeah, it's okay. It's a positive number and putting a square there doesn't matter, but anyway, yeah, okay, fine. See, you write it as W transpose W because when you take the derivative, right, with respect to vectors, it's easier to write it as 2 times W and cancel that 2 out. That's why you need that 2 also. Algebraically it works out nicely. Okay. Now, okay, KKT. There's an interesting story why there are 3 names to these particular conditions. There are 3 different people, they did not collaborate. Yeah, there are 3 people, no? It's I mean, I don't narrate the story, you look at it, it's very interesting. Okay. Yeah, the first condition is that the gradient of the Lagrangian with respect to the optimal parameters and optimal Lagrangian multipliers has to be 0, correct? This is the first one. The second one is that all the optimal Lagrangian multipliers have to be non-negative. And the third one is the product of the Lagrangian multipliers with the constraints. This has to be 0, correct? These are the 3 conditions. Okay. Okay. So let us apply all this and see what happens. The first one, which is the derivative of this with respect to, come again, where? Here. True. The derivative of this with respect to L has to be 0. This implies, I'll skip the algebra, please do it. So which means W star will be given by mu I star yi xi. Please do the algebra. Take the Lagrangian and take the derivative of it, which actually you can see it very simply, right? If you take the derivative of this with respect to W, there will be a W here, right? And this mu term will go away. and y w transpose xi term is around, right, and mu I will get multiplied and w will go away. Therefore, what survives is only mu I star yi times xi, that is it, it is simple. See, this is a very interesting equation. This fine, we already got our optimal w. What is the optimal w? Optimal w is simply a linear combination of multiple data points, that is it. You see this? We will do it now, we will do it. So this simply says, this is a, remember this is a very strong result, that the optimal w is simply a linear combination of data points, because this y is simply +1 or -1, right, and mu I are some constants, are scalars, Lagrange multipliers are scalars. So this is saying that my optimal w is a linear combination of xi. In fact, we will see that it will not be a linear combination of all xi's, because for some xi's this mu I will be 0. So this is a linear combination of all those data points for which mu I is non-zero, and those data points are called support vectors, and you will see that those data points are the ones that lie on margin. We will see that algebraically when we do that, but basically the idea is that the optimal parameters is simply a linear combination of a few data points scaled by the Lagrange multipliers, okay. And as he said, we will have to take a derivative of this with respect to b as well. So this will imply that the product of we will use this result later. The second constraint is simply that all mu i's have to be greater than or equal to 0 for all I, and the third condition is actually I have already written it there, okay, fine. Now, so define a set S which is a set of all xi's for which the Lagrange multipliers are non-zero. See, we know that Lagrange multipliers, right, one of the KKTs tells you that the Lagrange multipliers all have to be non-negative. I mean, they can either be 0 or positive. Now, let us consider all those xi's for which the Lagrange multiplier is strictly positive, okay. Now, this implies that my optimal decision boundary is simply a linear combination of the vectors in that set, isn't it? See, look at this, right, I mean I actually already mentioned it, that the ones for which mu I star is 0 will anyway go away. The only things that will survive are the ones for which this is strictly positive, and those vectors are called support vectors, okay, for which the Lagrange multipliers are positive, okay. Now what should we do? To find the final decision boundary W star, we need to find the optimal Lagrange multipliers. Come again, mu I star, yeah, we will have to find the optimal Lagrange multipliers, okay. Any questions so far? Okay, good. Now to get W star, we need the optimal Lagrange multipliers mu I star, okay. Now to find mu I stars, we solve the dual problem. Okay. Is there anybody who does not know what duality is in optimization theory? Okay, there are a few people. Okay, let me just quickly tell you what it is. if you solve a constraint optimization problem, right, how do we do it? There is a problem and there are some constraints. So we change that constraint optimization problem into an unconstrained optimization problem by writing this thing called Lagrangian, right. Now there is, for this is called the primal problem, okay, which is the Lagrangian function that we are optimizing. So this Lagrangian, as we saw, will be a function of two things. One, the optimization variable, and the Lagrange multiplier, which are constants. This is the generalized version of whatever we saw right now, is that to solve any constraint optimization problem, the optimal solution will be a function of the optimal Lagrange multiplier as well. So remember, when I said that putting a penalty on the norm of the parameters as a regularizer is equivalent to a Lagrange is solving a optimization problem, and I told you that here we do not search for optimal Lagrange multiplier, but we treat it as a hyperparameter. That is not the best way to solve the problem, because there exists an optimal Lagrange multiplier, okay, as we saw here. So there is a mu star here, which is an optimal Lagrange multiplier that gives you the exact solution for the primal problem. Now how do you get the optimal Lagrange multiplier? It is by solving another optimization problem, which is called the dual optimization problem, where the Lagrange multiplier becomes the variable for optimization. Okay, so every primal problem, a constrained primal problem, will have a corresponding dual to it, and their solutions are related. That is what a dual problem is. So that is duality of optimization problem. So why do we need to resort to duality? Is because in some cases solving the primal problem is easier. In some other cases solving the dual is easier. So in this particular context, solving dual is easier, is what we will see. In fact, again, referring back to my next course, there is one class of algorithms, okay, generative algorithms, called optimal transport. You might have heard of name called Wasserstein's-Gyan or W-Gyan. There is a problem called optimal transport, okay. It is an optimization problem. All problems, most problems in optimal transport are solved in the dual domain. Okay, so this duality is an important idea there. Okay, so we have to solve the dual problem to find the mu I star. So how do we solve the dual problem? So let us look at what duality is first. Now we have the primal problem, which is let us say that it is some function of w, and okay, let me not introduce new notations. I will write the entire problem itself here. Hold on. Okay, this is the problem that we have. Now define a dual function first. Dual function q, okay, which is a function from Rn to R, where n is the number of Lagrange multipliers. The dual problem, dual function will always be a function from Rn to R, where n is the number of Lagrange multipliers, always. Okay, so how do you define that? Q mu is the infimum over the Lagrangian, and this infimum is obtained over the optimization variable of the primal problem. What is infimum? No. Argmin is the minimizer, so min is the minimum. What is infimum? There's a name for it, right? I mean, it's the least upper bound. So basically, what is the difference between minimum and infimum is minimum can be achieved, infimum may not be achieved. That's it. say for, I mean, if there is a set whose minimum you can find, it is a function whose minimum you can find out over a particular set, then it's minimum. So you cannot find that minimum but it exists, and it's called infimum, that's it, okay. So you will have to find the infimum. I mean, see, most of the problems you can actually write this as minimum if you can minimize this with respect to W, but the most generalized way of writing it is in terms of infimum, that's it. So you will have to, so now note that this becomes a function of mu. Why? Because we are optimizing with respect to W here, right. We find out that function of, I mean, that point in the space of W and mu, that with respect to W. So this function L is a function of both W and mu, correct. So we navigate through the W space and find the value of this L for which it is minimum in the W space. So that becomes a function of mu, that's it. So that's the dual function. Is it the greatest lower bound or the least upper bound? Yeah, it is the greatest lower bound, correct, yeah. See, there are a few things that never get to my mind. So one of this is this false positive, false negative, type 1, type 2 error. The other thing is infimum and supremum. I know what they are, but are they the greatest lower bound or the least upper bound? I'll have to think about it before I get it right. Okay, so it's the greatest lower bound. Fine. Okay, so this is the dual function. We'll have to define what is called as a dual optimization problem. Okay, so construct the dual optimization problem as follows. So we'll have to maximize. So please note that if primal is a minimization problem, dual will be a maximization problem and vice versa, right. So because the primal that we have written is a minimization problem, the dual will be maximization. Maximize this dual function, okay, with respect to the Lagrange multipliers, subject to the fact that the Lagrange multipliers are non-negative, that's it. So this is the dual problem. Now what we should do is that we will have to write first construct the dual function, okay, and then we will have to solve this dual problem. That is what we will do right now, okay. Here, assuming that it can be achieved, in this particular case at least it can be achieved, okay. So this is what we should solve. To solve this, we need something called the primal dual relationship. See, all these have rigorous proofs, okay. I'm just using them, assuming that people have the background in optimization theory. So what it says is W star is, okay, W star and mu star are optimizers for primal and dual respectively. If and only if one, so W star and mu star are feasible for primal and dual respectively. I didn't define feasibility. Okay, feasibility means that you take that particular value, all the constraints are satisfied with that. Okay, so that's called feasibility. So both of these have to be feasible. Okay. and we have the minimizer of the primal problem is the minimum of the, this is obvious, right, because this is how we construct the dual. So if we take the Lagrangian, okay, and evaluate that at the minimizer the minimizer of the primal and the dual problem, it is equal to evaluating the dual function, okay, at its minimizer after being minimized with respect to W. That's it. I mean, obvious, right, because this is how we defined our dual function. When we solve it, this is how it has to be. What is max? No. See, this is the definition of the dual function, right? This infimum. This infimum is what I am writing as minimum there. Right? You minimize with respect to W. See, dual problem is maximizing with respect to mu. See, here I am writing the optimizer or the Lagrangian evaluated at the optimizer of the primal and the dual problem is equivalent to evaluating the dual function, okay, at mu star after minimizing with respect to W. That's correct. Okay. Okay. So this is how you construct the dual problem. I mean the dual function. First you have to start with construct the dual function by minimizing over W. That gets you the dual function, and then you maximize the dual function with respect to Lagrange multipliers, which is the dual problem. Which one? Yeah, Q is a function of mu. See, first you minimize with respect to W, right, and then okay, so perhaps I should write it this way. Hold on. I mean, I see what the confusion is. Let me write it this way. Hold on. Can actually write it as, so you take a minimum of the Lagrangian with respect to W. This is okay, no? I mean, minimizing L with respect to W will give you Q, okay, and then you evaluate that Q at mu star. That's what I meant. Okay, so I think this is a good time to stop this particular discussion. We'll stop here, and next class what we should do is we should actually construct the dual optimization problem and solve the dual problem, and solving this dual problem will give us an optimization over mu, and that I said will be solved using standard solvers to get the mu star and plug it back to the primal problem to get the optimal discriminant function. So after that we will go to the not linearly separable case. Then we will look at kernel machines, right? When the kernelized version of SVM, which will end the discussion on SVM. Okay, thank you.